Right now, a telescope the size of a tennis court is drifting nearly 1 million miles from Earth, staring into a darkness so deep that the light arriving at its mirrors left its source before our planet existed. And what it is finding there is not what anyone expected. James Webb has spotted galaxies that are fully formed, massive, and already old, just 400 million years after the Big Bang. That should be impossible under every model we have. It has detected light stretched so far across time that it carries the signature of physics behaving differently than the laws we learned from. And the deeper it looks, the more the universe seems to be pushing back against everything science assumed was settled. We are going to travel to the edge of what James Webb can see. We will visit the ancient galaxies that should not exist, the black holes that grew too fast, the voids so empty they defy explanation, and the single crack in the foundation of physics that no one has been able to close. We will see what the Hubble tension really means, why dark energy is no longer a constant, and what the oldest light in the universe is hiding inside it. If you enjoy this journey, feel free to like and subscribe. It genuinely helps this channel reach people who love real science. Take a breath. We are going to the edge of everything. For 30 years, one telescope defined the edge of the known universe, and then James Webb made it look small. The Hubble Space Telescope gave us the deep field, a tiny patch of sky no bigger than a grain of sand held at arm's length, containing over 3,000 galaxies. Each one a full galaxy with hundreds of billions of stars captured in a single long exposure. Astronomers called it one of the most important images ever taken. It showed us how far back in time we could see, and for a generation, scientists believed that was it. That was the limit. Hubble sees visible light and some ultraviolet. It was built for that, and for decades it worked beautifully, pushing the boundary of what we could observe further and further back in time. The most distant galaxies Hubble confirmed were sitting at redshifts that placed them around 400 million years after the Big Bang. That was already breathtaking, already almost beyond imagination. Here is what redshift means for those hearing the term for the first time. When a galaxy is moving away from us, or when space itself is stretching, the light it emits gets pulled and stretched too. It shifts toward the red end of the spectrum. The more stretched the light, the farther away the source. The farther away, the further back in time we are looking. A high redshift galaxy is ancient. We are seeing it as it existed billions of years ago in a universe that looked nothing like ours today. Hubble could measure this up to a point. Past a certain distance, the light was stretched so far it fell into the infrared range, invisible to Hubble. A wall. James Webb was built specifically to see through that wall. Its mirrors are nearly 22 feet across, almost 3 times wider than Hubble's. Its detectors are tuned to infrared wavelengths. It orbits nearly 1 million miles from Earth, far beyond the Moon, in a region cold enough to keep its sensors from being blinded by their own heat. Every design choice was made for one purpose: to see what Hubble could not. When the first full science images came back in July 2022, the reaction inside the scientific community was not quiet satisfaction. Several astronomers described it openly as disorienting. One team member said it felt like the universe had handed them a problem they did not know how to solve. The galaxies were there. Massive, structured, clearly formed, and they were sitting at distances that placed them in the first few 100 million years of cosmic history. Under every model astronomers had built over decades, this should not have been possible. Galaxies require time. They form from clouds of hydrogen that slowly collapse under gravity, ignite into stars, live through generations of stellar birth and death, and gradually accumulate mass and structure. The process takes hundreds of millions to billions of years, according to every simulation ever run. James Webb found galaxies that appeared to have skipped that process entirely, and the deeper it looked, the more of them appeared. What came next would push the mystery even further, because these galaxies were not just massive, they had properties that raised a question no one had a clean answer to. A question about the very engine that built them. That engine is the next piece of the story. The universe was dark for a very long time after it was born. Then, slowly, the first lights switched on, and James Webb is showing us that moment in detail for the first time. After the Big Bang, the universe spent hundreds of millions of years in a state astronomers call the cosmic dark ages. Space was filled with hydrogen gas, opaque and uniform. No stars, no galaxies. Just a vast, slowly cooling fog. Then, gravity began to do its work. Gas clouds collapsed. Temperatures rose at the centers. Fusion ignited. The first stars were born. These first stars were nothing like the ones we see today. They were enormous, hundreds of times more massive than our own star. They burned hot and fast and violent. They lived for only a few million years before exploding as supernovae, seeding the surrounding gas with heavier elements for the first time. Carbon, oxygen, iron, the ingredients that everything else would eventually be made from. This era is called the Epoch of Reionization. It is the period when the first light burned through the fog of neutral hydrogen and the universe became transparent. Astronomers knew it happened. They could see its fingerprints in the ancient light that fills all of space, but they had never seen inside it clearly. James Webb changed that. Using its infrared sensitivity, the telescope began detecting galaxies from deep inside this fog-burning era. Galaxies that are so distant, their light is only now arriving after traveling for over 13 billion years. And what the telescope revealed inside this period was unexpected. The reionization process, which models suggested should have been gradual and relatively uniform, appears to have been patchy. Some regions of the early universe cleared faster than others. Some pockets of space were transparent, while neighboring regions were still opaque. James Webb is mapping this uneven burning in a way no previous instrument could manage. That already changes our picture of early cosmic history. But the deeper surprise was not the patchiness. It was the galaxies themselves sitting inside this era. Several of the confirmed early galaxies James Webb has found are producing new stars at a rate that is extraordinary compared to what the standard model predicts for that time. One confirmed galaxy from around 400 million years after the Big Bang is forming stars at a pace that, if maintained, would double its stellar mass in only a few tens of millions of years. For context, our own galaxy forms roughly one new star per year at its current quiet pace. This is a galaxy on fire, a galaxy building itself at a speed the physics of the time should not have allowed. The fuel required for that kind of star formation has to come from somewhere. Gas has to collapse. Hydrogen has to be available in enormous quantities. The question scientists are now working through is whether the early universe was simply better at concentrating fuel than the models assumed, or whether something else was driving the process. One candidate sits at the center of many of these early galaxies. Something enormous. Something that grew far too fast for the timeline to comfortably explain. And what James Webb found inside those galactic cores sent a second wave of confusion through the astronomy community. That confusion has a name, and it is one of the most unsettling findings the telescope has produced so far. A galaxy takes time to build. At least, that is what every model said. Then James Webb found a collection of them that apparently did not get that message. The standard model of galaxy formation is called lambda cold dark matter. It is the result of decades of observations, computer simulations running on some of the most powerful machines ever built, and theoretical work by thousands of physicists across multiple generations. It describes how the universe went from smooth and uniform to the rich, structured web of galaxies we see around us today. The process starts with dark matter, invisible, unable to emit or absorb light, but massive enough to create gravitational wells. Normal matter, mostly hydrogen gas, falls into those wells. It cools. It collapses. It forms the first small structures. Those structures merge over time into larger ones. Small galaxies combine to form bigger ones. The process is called hierarchical assembly, and the key word is time. It takes time. Billions of years. James Webb found galaxies at redshifts corresponding to the first few 100 million years of the universe's existence that have already completed significant portions of this process. They are large. They are structured. Some have already stopped forming new stars, which means they went through a whole cycle of growth and shutdown in a universe that was barely a teenager by cosmic standards. One confirmed discovery: a galaxy observed at a redshift, placing it around 500 million years after the Big Bang, has a stellar mass comparable to the Milky Way. Our galaxy has had over 13 billion years to accumulate that mass. This galaxy did it in a tiny fraction of that time. When a team of researchers first published these findings, other scientists pushed back. The numbers seemed wrong. The instruments were new. Maybe the redshift measurements were off. Maybe the mass estimates were inflated. This is how science works, and the skepticism was appropriate. Then more galaxies appeared. And more? Different teams, different methods, different regions of the sky. The pattern held. One study published after James Webb's first year of science operations found a sample of galaxies so massive for their age that the authors openly stated the standard model could not account for them without significant modification. The paper went through peer review. It was confirmed. The term that started appearing in discussions was impossible galaxies. Scientists do not use that word lightly. What could explain them? Several theories are being actively tested. One proposes that the efficiency of star formation in the early universe was dramatically higher than current models allow. Another suggests that the initial conditions after the Big Bang were not as uniform as assumed, allowing some regions to get a head start on structure formation. A third, more radical option is that some of the physics governing how matter behaves at extreme density and extreme temperature in the early universe is simply wrong in the current models, that the equations need to be updated. None of these have been ruled out. None have been confirmed. What is confirmed is that the galaxies exist, that they are where James Webb says they are, and that standard cosmology does not comfortably explain them. And if the galaxies themselves were not enough, what is powering their cores makes the problem significantly worse. The engines at the heart of these early galaxies were running at a scale that raised an entirely separate set of questions. Questions about black holes and the limits of how fast they can grow. There is a speed limit in the universe, not just for light, for growth itself. And James Webb is finding objects that appear to be breaking it. When a gas cloud collapses to form stars, the process is not perfectly efficient. Stars are born, and as they form, they release enormous amounts of energy back into the surrounding gas. Radiation, stellar winds, eventually supernovae. All of that outward energy pushes against the inward collapse of more gas. This feedback mechanism acts as a natural brake. It limits how fast a region can convert raw material into stars. Astronomers built this brake into their models. It is not optional. Remove it, and the simulations break down in ways that contradict observations of nearby galaxies. The brake is real. The physics behind it is well tested at the scales we can study close to home. Now, move back to the early universe. The galaxies James Webb is finding in the first few 100 million years appear to have been forming stars at rates that should have triggered this brake mechanism hard and fast, slowing everything down. Instead, the growth continued. The mass accumulated. Think of it like this. Imagine a bonfire that is supposed to self-regulate. Every time the flames grow too large, the heat pushes the fuel away, so the fire shrinks back. That is the stellar feedback loop. Now, imagine watching a fire that keeps growing regardless, piling on fuel faster than the heat can push it away. That is what James Webb is seeing in some of these ancient galaxies. One possible explanation that has gained traction is that the early universe's gas had a higher density of cold, dense filaments flowing directly into galactic cores. Cold streams, they are called in the literature. These streams could theoretically bypass the feedback mechanism, delivering raw material to the center of a galaxy faster than the stars could push it away. This is a confirmed theoretical concept. Whether it scales to what James Webb is observing is still an open question. Another explanation involves the role of dark matter halos. In the early universe, dark matter may have been distributed in ways that created unusually deep gravitational wells, pulling gas inward with a force that overwhelmed the stellar feedback. This too is theoretical, and the math is being actively worked on. What is confirmed is the observational result. These galaxies grew faster than current physics comfortably allows. Multiple independent research teams have checked the data. The conclusion keeps holding. The implications reach beyond the galaxies themselves. If the standard feedback model is wrong for the early universe, it means every simulation of cosmic history built on that model is, at least partially, incorrect. The entire timeline of how the universe became what it is today would need revision. That is a significant statement. Scientists do not make it casually. And here is the part that adds another layer of urgency to all of this. The growth rate problem is not just about stars. It is also about what sits at the centers of these galaxies. Objects that grew even faster than the galaxies surrounding them. Objects that, according to every known physical limit, should have taken far longer to reach their observed size. The next chapter is about those objects, and what James Webb found inside them has physicists genuinely reconsidering some very old assumptions. Every galaxy James Webb observes is measured by a single critical number. That number is its redshift. And in several cases, the redshift is producing answers that do not fit the map. Redshift is the most reliable tool astronomers have for measuring cosmic distance and age. It works because of a simple physical principle. When a source of light moves away from you, the light waves it emits are stretched. They become longer. Longer light waves sit toward the red end of the visible spectrum. The more the light is stretched, the higher the redshift value. The higher the redshift, the more the universe has expanded since that light was emitted. Since the expansion rate of the universe can be calculated, a redshift value translates directly into a distance and a look-back time. A galaxy with a redshift of 2 is being seen as it existed roughly 10 billion years ago. A redshift of 8 puts us over 13 billion years back. A redshift of 13 reaches back to the first few 100 million years. This is the core measurement that makes all of James Webb's early universe findings possible. The issue is what the measurements are revealing when combined with other data about the same objects. Several galaxies James Webb has confirmed at very high redshifts show properties that are internally inconsistent with their measured age. The stellar populations inside them, the mix of young and old stars, the chemical composition, the distribution of heavier elements, all tell a story of a galaxy that has been evolving for longer than the timeline allows. It is similar to meeting someone who claims to be 20 years old, but whose physical condition, professional accomplishments, and family history all suggest they have lived for 50. Each piece of evidence on its own might have an explanation. Together, they form a pattern that is harder to dismiss. Some researchers have proposed that the very earliest periods of cosmic history moved faster than current cosmological models allow, that the universe had a phase of accelerated growth not captured in the standard timeline. This is an active area of theoretical work, and it connects directly to questions about the nature of dark energy and inflation. Others have suggested that the initial mass function, The distribution of star sizes in early star-forming regions was weighted heavily toward massive stars. Massive stars live fast and die young, producing large amounts of heavy elements quickly. A galaxy seeded with many massive stars early on would appear chemically older than a galaxy of the same age, seeded with smaller, longer-lived stars. This could explain some of the inconsistencies without changing the fundamental timeline. What is confirmed is the inconsistency itself. The data from James Webb is producing galaxies whose measured redshift and whose internal properties are in tension. The tension is real. The explanation is not yet settled. And the redshift problem does not stand alone. It connects to something larger, a disagreement that has been quietly growing in cosmology for over a decade. A disagreement so fundamental that it has been called the most serious crisis in modern physics. That disagreement has a name, and James Webb just made it significantly harder to ignore. The universe is expanding. That has been known since the 1920s. What has never been settled is how fast it is expanding right now. And the answer to that question is tearing cosmology apart. The rate of cosmic expansion is measured by a number called the Hubble constant. It tells astronomers how quickly galaxies are moving away from each other per unit of distance. It is one of the most important numbers in all of science. It determines the age of the universe. It shapes our understanding of dark energy. It sets the scale for everything else in cosmology. For decades, measuring the Hubble constant was the goal. Teams of astronomers spent careers refining the number. By the early 21st century, two independent methods had emerged as the most reliable. Both were rigorous. Both had been cross-checked extensively, and they disagreed. The first method looks at the early universe. It analyzes the oldest light in existence, the cosmic microwave background, the faint glow left over from just 380,000 years after the Big Bang. By studying the patterns in that ancient light using the Planck satellite, scientists calculated what the Hubble constant should be. Their answer was around 67 kilometers per second per megaparsec. The second method looks at the nearby universe. It uses standard candles, objects whose true brightness is known, to measure distances across space. The most reliable of these are a type of exploding star called a type Ia supernova. By comparing how bright the explosion appears against how bright it actually is, astronomers calculate how fast the universe is expanding today. This method consistently produces an answer closer to 73. Those two numbers sound close. They are not. The gap between them, when measurement uncertainties are factored in, represents a genuine physical discrepancy. Either one method has a systematic error no one has found, or the universe is actually behaving differently in its early and late stages. The second option would require new physics. James Webb was expected by some researchers to resolve the tension. If a measurement error existed in the nearby universe method, Webb's sharper observations might expose it. Instead, early results from James Webb confirmed and in some cases sharpened the measurements supporting the higher expansion rate. The tension has not closed. This matters for everyone. If the universe is expanding faster than the early universe models predict, dark energy, the force thought to be driving the acceleration, is either stronger than assumed or behaving differently over time. It reshapes our understanding of what the universe is made of and where it is going. Several alternative models are now being seriously explored. Some propose an early phase of dark energy that briefly dominated the universe before fading. Others suggest dark energy evolves with time rather than remaining fixed. What is confirmed is the disagreement. What remains unknown is what causes it. And as the expansion debate continued, James Webb turned its attention to something even older, something at the very beginning of time, preserved in a faint glow that fills all of space. What it found hiding inside that ancient light had been overlooked for decades, and the signal it uncovered is changing the conversation in ways no one predicted. Two different teams of scientists, using two completely different methods measuring the same universe. One says it is expanding at one speed. The other says it is expanding significantly faster. And after decades of work, neither can find the error in the other's math. To understand why this is so deeply unsettling, think about what cosmology is trying to do. It is building a complete, consistent model of the entire universe, from its first moments to its final fate. Every number in that model has to agree with every other number. The model is only as strong as the consistency of its measurements. The Hubble constant is one of the load-bearing numbers. If it genuinely takes two different values depending on which era of the universe you are measuring, then the model has a crack running through its foundation. The early universe measurement comes from the cosmic microwave background data. This light was emitted when the universe was just 380,000 years old, before any stars or galaxies existed. The patterns encoded in it are exquisitely sensitive to the conditions at that time, including the density of matter, the density of dark energy, and the rate of expansion. When scientists fit the standard model to this data, the Hubble constant comes out at around 67. The late universe measurement uses what is called the cosmic distance ladder. It starts with parallax measurements for nearby stars, then uses those to calibrate the brightness of a pulsing star called a Cepheid variable, then uses those to calibrate the brightness of type Ia supernovae, which can be seen across billions of light years. Each rung of the ladder is calibrated against the one below it. The final number comes out consistently around 72 to 73. The difference is roughly 9%. In everyday life, 9% might seem minor. In precision cosmology, it is enormous. Researchers have checked both methods for errors exhaustively. The Cepheid calibration has been redone with James Webb, which can see these pulsing stars much more clearly than Hubble could in crowded, distant galaxies. The result still comes out high. The discrepancy persists. What this means, if both measurements are genuinely correct, is that something changed in the universe's history. Some component of the cosmos that was present early either faded away or grew stronger over time, altering the expansion rate in a way no current model accounts for. One theoretical proposal is called early dark energy. It suggests that a brief burst of dark energy pushed the expansion rate higher before dissipating. Another theory involves a different form of dark matter that interacted with regular matter early on before becoming inert. A third possibility is that general relativity works slightly differently over the largest cosmic scales. None of these are confirmed. All are being actively tested. Several of the early universe galaxies James Webb has found sit in the middle of this tension. Their properties are sensitive to the expansion rate, assumed during the era when they formed. As James Webb maps more of them, it is providing new data that every competing model has to account for. And the data keeps getting stranger, because while scientists debate the Hubble constant, James Webb has been detecting something unusual hiding inside the oldest structure in existence. The oldest light in the universe is not coming from a star, it is not coming from a galaxy. It is everywhere at once, filling all of space equally, a faint glow left over from a moment when the universe was less than 400,000 years old. It is called the cosmic microwave background, and James Webb, combined with previous data from the Planck satellite, is revealing things inside it that were too subtle to detect before. The cosmic microwave background was first detected in 1965 by accident. Two researchers at Bell Telephone Laboratories were trying to eliminate a persistent background noise from their antenna. They checked for pigeons nesting in the equipment. They cleaned the dish. The noise remained. Eventually, they realized they were hearing the afterglow of the Big Bang itself, arriving from every direction simultaneously. This glow has been cooling for over 13 billion years. Today, it sits at a temperature of about 2.7 degrees above absolute zero. To sensitive microwave detectors, it is the most detailed record of early cosmic conditions we possess. The tiny temperature variations across this glow, regions that are fractionally warmer or cooler by amounts smaller than 1 part in 100,000, represent the seeds of all structure in the universe. Every galaxy, every cluster, every filament of the cosmic web grew from those seeds. James Webb does not observe the microwave background itself. Its instruments are tuned to infrared, designed for the light of ancient galaxies. But everything James Webb finds about those ancient galaxies has to be consistent with the microwave background data. Every galaxy it discovers at high redshift is a test of whether the universe that produced the background pattern could also produce the structures we see. So far, several of James Webb's findings create tension with what the microwave background predicts. The abundance of massive early galaxies, the star formation rates, the level of structural development in the early cosmic web, all of these are higher than what the microwave background data, run through the standard model, would suggest should exist at those times. This is a tension, not a contradiction. The difference matters. A contradiction would mean one dataset is simply wrong. A tension means both datasets may be right, and the model connecting them is what needs to be refined. One area of active research is the primordial power spectrum, the distribution of how strong the density fluctuations were across different size scales in the early universe. The microwave background measures this spectrum across large scales very precisely. What James Webb is adding is information about small scales, the scales at which individual galaxies formed. If the power spectrum has more energy at small scales than the standard model predicts, it would help explain both the microwave background data and the unexpectedly developed early galaxies simultaneously. But inside the microwave background itself, one anomaly has resisted every explanation offered so far. An anomaly that hints at something about the shape of space itself, something that, if confirmed, would change everything. Keep going. The universe is about to get stranger. When the scientific team behind one of James Webb's first confirmed discoveries announced their result, other astronomers looked at the data and asked the same question. How is that there? The galaxy is designated Glass Z 13 in scientific literature. For this story, call it the Breaker. It earned that name by existing in a place and at a time when nothing like it should have been able to form. The Breaker sits at a redshift that places it just over 300 million years after the Big Bang. When its light left the galaxy and began its journey toward us, the universe was less than 3% of its current age. The first stars had only recently begun to form. The building blocks of galaxies were just beginning to assemble, and yet the Breaker was already there, already a structured galaxy, already containing hundreds of millions of stars. The initial detection came from James Webb's infrared imaging. The galaxy appeared as a faint smudge, but one with a spectral profile that immediately drew attention. The way its light was distributed across infrared wavelengths was consistent with a high redshift measurement. Follow-up spectroscopic observations, which spread the light out into its component wavelengths to get a precise redshift reading, confirmed the number. The team was careful. They published their findings and invited scrutiny. Other groups checked the data independently. The redshift held, the distance held. The existence of this galaxy at this moment in cosmic history is, as of the current state of science, confirmed. What is not confirmed is what it means. The stellar mass of the Breaker, the total mass of all the stars it contains, is estimated in the range of several 100 million times the mass of our own star. That sounds enormous. Compared to the Milky Way, it is relatively small. The Milky Way contains several 100 billion stars. Put it in context though. In the standard model, a galaxy of even that size should not have had time to assemble its mass in the first 300 million years. The simulations say so clearly. To build that much stellar mass from the density of matter available in the early universe using the star formation rates the models predict, you would need far more time than the timeline allows. Something ran faster than the physics allows for, or the physics is incomplete. The breaker was not the only discovery of this kind. Within the first year of James Webb operations, a collection of high redshift galaxy candidates were identified, some at even more extreme distances. Some of these are still awaiting full spectroscopic confirmation, but the sheer number of candidates and the consistency of their properties has made it increasingly difficult to explain the collection as measurement error alone. One astronomer described it publicly as finding several cities fully built on land that the geological record says was under the ocean at the time. The problem goes beyond galaxy mass. The chemical composition of these early galaxies, specifically the presence of heavier elements like carbon and oxygen, indicates that multiple generations of stars had already lived and died before these galaxies were observed. Each stellar generation takes time. Multiple generations take more time that the timeline does not easily provide. The breaker sits at the center of a growing body of evidence that the standard picture of how structure formed after the Big Bang needs revision. The scale of that revision is still being determined. And there is one more thing the breaker is telling us. Something about the black hole at its center that makes the timeline problem even harder to resolve. The universe is not a uniform cloud of galaxies scattered randomly through space. It is a web, a vast, three-dimensional structure of filaments, sheets, and nodes, with enormous empty regions between them, and near the edge of what James Webb can observe. That web begins to look different in ways that are forcing scientists to reconsider how structure itself formed. The large-scale structure of the universe was not designed. It emerged. In the very early universe, tiny quantum fluctuations existed in the density of the hot plasma that filled all of space. Regions that were fractionally denser pulled in more matter through gravity. Over billions of years, those overdense regions grew into filaments and walls of galaxies, while the underdense regions became voids. The result is a structure often compared to a sponge or a cosmic foam, visible in three-dimensional galaxy maps that astronomers have built over decades. This structure is called the cosmic web. Every major theory of cosmology has to be able to reproduce it, starting from the initial conditions after the Big Bang. The problem James Webb is uncovering is that the web appears to be more developed, more structured, and more differentiated in the very early universe than the models predicted it should be at that time. When you look at a region of the universe from nearby, what you see is the result of over 13 billion years of gravitational evolution. Filaments are thick and well-defined. Voids are large and genuinely empty. Clusters at the nodes of filaments contain thousands of galaxies each. The structure is pronounced. Look back to when the universe was less than 1 billion years old, and models expected to see the web in a much earlier, fuzzier state. Overdense regions beginning to collapse, the first hints of filaments forming, clusters just starting to gather mass, a universe in its structural infancy. James Webb is seeing something more mature than that. Several of the earliest confirmed galaxy clusters and protoclusters found by the telescope show signs of organization that models place much later in cosmic history. The galaxies within these early groups are already showing the kinds of positional correlations, the tendencies to cluster along certain directions and avoid certain regions, that in nearby structures took billions of years to establish. One particularly striking observation involved a chain of galaxies at very high redshift, aligned along what appears to be an early cosmic filament. The alignment was sharper and more defined than simulations of that era typically produce. This either means the simulations are missing something, or the initial density fluctuations after the Big Bang were distributed differently than assumed. The distinction matters deeply. If the primordial fluctuations were different, then the seeds from which all cosmic structure grew were different. The entire evolutionary history of the universe, every galaxy, every star, every planet, traces back to those initial conditions. Getting them wrong means every model built on them carries that error forward. Scientists are now running revised simulations, adjusting the initial conditions to see which version better matches what James Webb is observing. Several early results suggest that the fluctuations may have had more power at small scales than the standard model assumes. But while theorists work on the simulations, James Webb has also been looking in a very different direction, not at the structure visible within the web, but at the forces pulling on the web from beyond it, forces that come from something no telescope has ever directly observed, something that sits beyond the edge of our visible universe entirely. And it has been pulling on us for a very long time. Not just through the slow drift of cosmic expansion, but being actively pulled in a specific direction by a gravitational force so enormous it is displacing thousands of galaxies across hundreds of millions of light years. And the source of that pull is something we cannot fully see. This force has been known about since the 1980s. Astronomers mapping the movements of nearby galaxies noticed that an enormous region of space, covering hundreds of millions of light years in every direction, is flowing together toward a specific point in the constellation Centaurus. The Milky Way is part of that flow. So are the galaxies around it, the Andromeda Galaxy, the Virgo cluster, and dozens of other large structures, all of them drifting, slowly but measurably, toward the same point. The point is called the Great Attractor. What makes it so strange is that the source of its gravitational pull sits partly behind the zone of avoidance, the dense band of dust and gas along the plane of our own galaxy that obscures observations across a significant portion of the sky. For decades, astronomers could not see directly into this region to find what was creating the pull. Radio telescopes helped. They can peer through the dust that blocks visible light. What they found behind the zone of avoidance was a massive supercluster of galaxies called the Norma Cluster, a dense region of galaxies and hot gas with a combined mass reaching into the quadrillions of times the mass of our own star. For a time, this was thought to be the answer. It was not the complete answer. Further analysis showed that the Norma Cluster, massive as it is, does not account for all of the flow. Something beyond it, something even farther away, is also pulling. That something was eventually identified as a structure called the Shapley supercluster, one of the most massive concentrations of matter in the observable universe. It sits over 500 million light-years away and contains thousands of galaxies in a region roughly 1 billion light-years across. Its gravitational influence reaches us over those enormous distances and contributes significantly to the overall flow. But even Shapley may not be the end of it. Recent analyses of galaxy flows using large survey datasets have suggested that the bulk motion of galaxies in our region of the universe is consistent with a gravitational influence coming from even farther away, from regions approaching or possibly beyond the edge of the observable universe. This is where the physics becomes genuinely uncomfortable. If something beyond our visible horizon is exerting a gravitational influence on matter we can observe, it raises questions about the nature of what lies outside the sphere of the universe we can see. According to the standard model, the observable universe is just one part of a much larger whole. What lies beyond our horizon is, by definition, unreachable by light in the age of the universe so far. But gravity, operating through the curvature of space-time, may carry information across distances that light has not yet bridged. This is confirmed as a theoretical possibility. Whether it is actually occurring, and whether the bulk flows we observe are genuinely responding to mass beyond our horizon, is still being investigated. James Webb is contributing to this investigation by improving our maps of galaxy distribution and motion at very high redshifts. The more precisely we can chart the large-scale flow of matter, the better chance we have of identifying where the pull is truly coming from. And what James Webb is finding about dark energy as it examines these distant structures is adding yet another layer of uncertainty. Because dark energy, the force that was supposed to be simple and constant, is beginning to look like neither. What comes next in this story may be the most consequential finding of all. For 25 years, cosmologists operated on a specific assumption about dark energy. It was constant, uniform, a fixed property of space itself, the same everywhere and at all times. The universe was accelerating its expansion, and dark energy was the engine, steady and unchanging. James Webb is providing new evidence that this assumption may be wrong. Dark energy was discovered in 1998 when two independent teams studying distant exploding stars found that the universe was accelerating. Galaxies are speeding away from each other faster and faster. Something is pushing them. That something was named dark energy, and it was folded into the standard model as the cosmological constant, a term Einstein had originally included in his equations and then removed, describing a fixed energy density belonging to empty space. The cosmological constant fit the data well for years. It predicted how the universe should expand, and observations confirmed those predictions to high precision. Dark energy seemed settled. Then the cracks appeared. The most significant new data comes from a project called the Dark Energy Spectroscopic Instrument Survey, combined with James Webb's observations of distant galaxies. Together, these tools are building the most detailed three-dimensional map of the universe ever assembled, tracking how galaxy clustering has evolved across billions of years. What the data is showing, still preliminary and still being challenged by multiple independent groups, is that the rate of cosmic expansion may not have been perfectly constant over time. There are hints that dark energy's strength varied, weaker in the earlier universe and growing over time. If confirmed, this would rule out the cosmological constant as the correct description of dark energy. It would mean dark energy is something dynamic, something that evolves. This matters for a specific reason. If dark energy changes over time, the fate of the universe changes too. A growing dark energy could mean the expansion accelerates without limit, eventually tearing apart galaxies, then star systems, then planets, then atoms themselves in an event called the Big Rip. A decaying dark energy might eventually reverse into collapse. The endpoints are radically different depending on which scenario is correct. Several theoretical frameworks have been proposed to explain a dynamic dark energy. One is called quintessence, a slowly evolving field that permeates space and changes value over time. Another involves modifications to general relativity at the largest scales. A third, more speculative framework connects dark energy's behavior to the seething energy of empty space at the quantum level. None of these are confirmed. The data is still being refined, but the possibility that dark energy evolves is now taken seriously enough that major observatories have reorganized their observing programs to test it. And as James Webb maps the boundary of the observable universe, it is finding that the farther it looks, the stranger the behavior of every fundamental force becomes. The patterns emerging from the data are nudging physicists toward a conclusion many had hoped to avoid: that the universe does not behave the same way throughout its history. The next chapter takes us to the very oldest signal the universe ever produced, and what is hiding inside it has been waiting to be found for decades. It is the most ancient signal we can detect, older than any star, older than any galaxy, a faint, cold glow that fills every corner of the sky and carries within it the complete fingerprint of the universe as it existed just moments after creation. Astronomers have studied it for decades, and James Webb is now helping reveal details inside it that previous instruments were too limited to capture. The cosmic microwave background was first detected in 1965 by accident. Two researchers at Bell Telephone Laboratories were trying to eliminate a persistent noise from their antenna. They checked for pigeons nesting in the equipment. They cleaned the dish. The noise remained. Eventually, they realized they were hearing the afterglow of the Big Bang itself, arriving from every direction simultaneously. This glow has been cooling for over 13 billion years. Today, it sits at a temperature of about 2.7 degrees above absolute zero. To sensitive microwave detectors, it is the most detailed record of early cosmic conditions we possess. The tiny temperature variations across this glow, regions that are fractionally warmer or cooler by amounts smaller than 1 part in 100,000, represent the seeds of all structure in the universe. Every galaxy, every cluster, every filament of the cosmic web grew from those seeds. Reading the pattern of those variations tells cosmologists what the universe was made of, how fast it was expanding, and what forces were shaping it at the moment this light was released. James Webb does not observe the microwave background directly. Its instruments are tuned to infrared, but everything James Webb finds about ancient galaxies has to be consistent with the microwave background data. Every galaxy it discovers at high redshift is a test of whether the universe that produced the background pattern could also produce the structures we see. So far, several of James Webb's findings create tension with what the microwave background predicts. The abundance of massive early galaxies, the star formation rates, the level of structural development in the early cosmic web, all of these are higher than what the microwave background data, run through the standard model, would suggest should exist at those times. One area of active research is the primordial power spectrum, the distribution of how strong the density fluctuations were across different size scales in the early universe. The microwave background measures this spectrum across large scales very precisely. What James Webb is adding is information about small scales, the scales at which individual galaxies formed. If the power spectrum has more energy at small scales than the standard model predicts, it would help explain both datasets simultaneously. And inside the microwave background itself, one anomaly has resisted every explanation offered so far. A region of the sky so large, so cold, and so statistically improbable that it has forced scientists to consider possibilities that sound like they belong in a different kind of story. The debate around it has been running for over a decade, and it has only sharpened with time. That anomaly is next. And it may be the strangest thing James Webb is circling. There is a region of the sky that is colder than everything around it, colder than statistical models of a random universe predict it should be. It covers an area so vast that the structure causing it must span close to 1 billion light-years. And after years of study, no one has closed the case on what it is. It is called the cold spot. It appears in the cosmic microwave background as a patch where the temperature is measurably lower than surrounding regions. The difference is small in absolute terms, but in the context of the microwave background, where temperature variations are already tiny, the cold spot stands out. Statistical analyses have put the probability of it occurring by random chance at well below 1%. That is low enough to treat it as a real feature. The most straightforward explanation is a supervoid, a region of space containing far less matter than the cosmic average. When light from the microwave background travels through an underdense region in an accelerating universe, it loses a small net amount of energy, producing a cooler patch in the background. A supervoid would create exactly that pattern. Several observational campaigns have searched for a supervoid in the direction of the cold spot. The results are mixed. Some surveys found evidence of a large, underdense region. Others found the underdensity too modest to fully account for the cold spot's temperature. The supervoid may be real, but not solely responsible. James Webb is contributing by observing galaxy distributions in the direction of the cold spot at redshifts that reach further back in time than previous surveys managed. Early results are consistent with a large void in the right location, though they do not yet resolve whether that void alone is sufficient. Two other explanations are on the table, each more dramatic. The first involves inflation, the period a fraction of a second after the Big Bang, when the universe expanded by an enormous factor in an incredibly short time. If inflation was not perfectly uniform, a quantum fluctuation during that period could have left an unusually large cold imprint in the background that persists today. The second explanation is the one discussed most cautiously. It proposes that the cold spot is a remnant of contact between our universe and another region of space, a scar from a bubble collision in a landscape of many universes generated during inflation. This idea has been published in peer-reviewed journals. It sits firmly in the category of a theoretical possibility, not a confirmed observation. The challenge is that it may never be fully testable. What is confirmed is that the cold spot exists, its scale is anomalous, and the leading mundane explanation does not fully account for it. And the cold spot is only one of the strange signals hiding in the ancient light. A broader pattern of directional asymmetry across the entire sky is now being debated. Scientists are asking whether the universe has a preferred direction, a subtle orientation that the Copernican principle says should not exist. And that question may be telling us something about the outer boundary of the universe itself. The next stop is even harder to explain. Everything we know about black holes says they form from dead stars. A massive star runs out of fuel, collapses under its own gravity, and leaves behind a singularity so dense that nothing can escape it, including light. That is the model. And James Webb is finding evidence that at least some black holes may have formed through a completely different process, one that predates the first stars entirely. These hypothetical objects are called primordial black holes. The idea is not new. Theoretical physicists proposed the concept decades ago, suggesting that in the extreme density of the very early universe, random fluctuations in the density of matter could have compressed certain regions past the threshold required for a black hole to form before any star existed, before any galaxy. In the first fractions of a second after the Big Bang, black holes may have spontaneously appeared throughout space. For years, the idea sat at the edge of mainstream physics. Interesting, but lacking observational support. Then two things happened. Gravitational wave detectors began confirming collisions between black holes unusually large compared to what stellar evolution models typically produce. And James Webb began finding supermassive black holes in the earliest galaxies at redshifts that make their existence deeply puzzling under standard formation theory. A supermassive black hole at the center of an early galaxy presents a timeline problem. These black holes contain masses equivalent to hundreds of millions to several billion times that of our own star. Growing a black hole to that size through normal accretion, the process of pulling in surrounding matter over time, takes far longer than the timeline allows. One proposed solution is that some of these supermassive black holes did not grow from stellar remnants at all. They grew from primordial black holes, objects that were already massive at the moment the universe became transparent, giving them a head start of hundreds of millions of years over anything that formed from a star. James Webb has been observing the environments around high redshift active galactic cores in detail that was not previously possible. In several cases, the properties of the surrounding gas and the luminosity of the central engine are more consistent with a black hole that seeded early and grew continuously than with one that formed late from a stellar collapse. This is a well-motivated theory supported by suggestive indirect evidence. It has not yet been proven observationally. What is confirmed is the problem the theory is trying to solve. Supermassive black holes existed too early for standard formation models to comfortably explain. James Webb has made this problem sharper than it was before the telescope launched. there is also a broader implication. If primordial black holes formed throughout the early universe, they could account for some or all of dark matter. A population of black holes spread through the cosmos in the same pattern as invisible dark matter could be pulling on galaxies without emitting any light. And the problem of early black holes connects directly to the most extreme examples of them. Objects so massive, so early, and so inexplicably powerful that they have been called the most challenging result in all of observational cosmology. Those are next. They are the brightest sustained objects in the universe, cores of galaxies where matter is falling into a black hole so massive, so fast, that the energy released outshines every star in the galaxy combined, often by a factor of hundreds. They are called quasars, and James Webb is finding them at distances that make their existence a serious problem for physics. A quasar is powered by accretion. Gas and dust spiral into a supermassive black hole. As the material falls inward, it forms a disk that heats to extreme temperatures and radiates across the entire electromagnetic spectrum. Radio waves, infrared, visible light, ultraviolet, X-rays, all at once, at luminosities detectable from across the observable universe. To produce that level of output, the black hole has to be enormous. Typical quasar black holes range from hundreds of millions to tens of billions of times the mass of our own star. The timeline problem is severe. A black hole grows by consuming matter. There is a physical limit to how fast it can do this. Pull in matter too quickly, and the radiation pressure from the heated disk pushes back against the infalling gas, slowing the process. This limit is called the Eddington limit. Even at the theoretical maximum, growing a black hole to several billion stellar masses from a stellar remnant would take well over 1 billion years. James Webb has confirmed quasars operating at full power before the universe was 1 billion years old. One confirmed quasar sits at a redshift, placing it less than 700 million years after the Big Bang, and its central black hole is estimated at several hundred million stellar masses already. Under the Eddington limit, reaching that size in that time is essentially impossible. The math does not work unless something outside the standard model is involved. Several explanations are being examined seriously. The first is super Eddington accretion, the idea that early conditions allowed black holes to pull in matter faster than the limit permits, perhaps because the surrounding gas was denser and the feedback mechanism less effective. There is theoretical support for brief periods of super Eddington accretion, but sustaining it long enough to produce these black holes is a separate challenge. The second explanation returns to primordial black holes. If some black holes formed directly from density fluctuations rather than stellar collapse, they could have begun with much higher seed masses. A third option involves direct collapse black holes. In regions of the early universe where star formation was suppressed, clouds of gas may have collapsed directly into black holes without passing through a stellar phase, producing seeds far more massive than stellar remnants. James Webb is measuring the environments, the gas compositions, and the surrounding galaxy structures of these early quasars in greater detail than any previous telescope. The clues are being gathered. What is already clear is that the standard picture of how black holes grow is incomplete, and the way astronomers measure distances across the universe, the very tool that confirms how far away these quasars are, is now showing signs of its own strain. What comes next is about the ruler itself starting to crack. To measure the universe, you need a ruler. Astronomers have built one over a century of careful work. It is called the cosmic distance ladder, and near the edge of the observable universe, that ladder is showing signs of strain that James Webb is making impossible to ignore. The problem starts with how we measure vast cosmic distances. You cannot stretch a tape measure across billions of light years. Instead, astronomers use objects whose true brightness they already know. If you know how bright something actually is, and you measure how bright it appears from Earth, The difference tells you exactly how far away it must be. These objects are called standard candles. The most important standard candle in modern cosmology is the Type Ia supernova. When a white dwarf star accumulates enough mass from a companion to reach a specific threshold, it detonates in a thermonuclear explosion. These explosions are remarkably consistent in their peak brightness. One Type Ia supernova in a distant galaxy glows with almost the same intrinsic luminosity as another in a completely different galaxy. This consistency is what makes them useful as rulers. The distance ladder depends on this consistency, and for decades it held beautifully. Then the cracks appeared. James Webb has observed Type Ia supernovae and the Cepheid variable stars used to calibrate them with precision that Hubble could not match. In dense, crowded galactic environments, Hubble's images sometimes blended multiple stars into a single point of light, slightly inflating the measured brightness of individual Cepheid stars. James Webb can resolve individual stars in these crowded fields cleanly. The expectation was that cleaner observations would close the Hubble tension. Instead, James Webb's sharper measurements confirmed the higher expansion rate. The Cepheid calibrations were not significantly inflated by crowding. The ladder is sound at that rung, but the disagreement remains. Other issues are emerging. A separate class of standard candle, surface brightness fluctuations in elliptical galaxies, is producing distance measurements that do not always agree with the Cepheid-based distances. In some cases, the discrepancies affect conclusions about the local expansion rate. Another concern involves the uniformity of Type Ia supernovae themselves. Recent studies using ultraviolet observations have found that these explosions in the early universe may differ subtly from those in the nearby universe. Older stellar environments produce different kinds of white dwarf progenitors. If the explosions are not perfectly uniform across cosmic time, the standard candle assumption introduces a systematic error that grows larger the farther back in time you look. This matters because the entire case for dark energy was built on Type Ia supernova measurements. If the candles are not perfectly standard, the conclusions built on them need to be re-examined. The distance measurement crisis is a precise identification of where the uncertainties are. That precision is necessary before the next generation of conclusions can be drawn, and those uncertainties connect directly to an even deeper question. What if the physical laws themselves are not perfectly constant across the vast reaches of the universe? That question is no longer purely philosophical. James Webb is finding hints that it may have a physical answer. The laws of physics are supposed to be universal. The same equations that describe the behavior of matter in a laboratory should describe the behavior of matter in a galaxy 10 billion light-years away. The constants in those equations, the strength of gravity, the charge of an electron, the speed of light, should be fixed quantities, identical across all of space and time. This assumption is so fundamental that it is rarely stated. It is simply taken as given. James Webb is giving scientists a reason to look at that assumption more carefully. Several independent lines of observational evidence suggest that at least one fundamental constant may not be perfectly uniform across the observable universe. The constant under scrutiny is the fine structure constant, a dimensionless number that governs the strength of the electromagnetic force. It determines how strongly charged particles interact with light. It shapes the structure of atoms and the chemistry that emerges from atomic interactions. The fine structure constant has been measured in laboratories with extraordinary precision. Its value is approximately 1 divided by 137. This number appears throughout physics and chemistry. It is one of the most precisely measured quantities in science. Astronomers can also measure it using the light from distant quasars. When that light passes through clouds of gas between the quasar and Earth, the gas absorbs certain specific wavelengths, leaving dark lines in the spectrum. The precise positions of those lines depend on the fine structure constant at the location of the absorbing gas. If the constant is the same everywhere, the lines should appear at exactly the positions calculated from laboratory measurements. Several studies of quasar spectra over the past 2 decades have found small but statistically significant shifts in these line positions in certain directions of the sky. When large samples are combined, a pattern has emerged, suggesting that the fine structure constant may be slightly larger in one hemisphere of the observable universe and slightly smaller in the opposite hemisphere. This has been called the dipole variation. If real, it would mean the electromagnetic force operates at slightly different strengths in different parts of the cosmos. The difference is tiny at human scales, but across cosmological distances, even tiny differences in fundamental constants compound into significant effects on how matter organizes itself. James Webb is observing quasar absorption systems at higher redshifts and with greater spectral precision than previous instruments could achieve. Early results are being analyzed. No definitive confirmation or refutation has been published as of the current state of science. What is confirmed is that the question is serious enough to be studied with the most powerful telescope ever built. Questions that are purely speculative do not get observing time on James Webb. If the fine structure constant varies across the universe, it would require new physics. The standard model of particle physics assumes all fundamental constants are exactly that, constant. A variation would suggest an underlying field that modulates electromagnetic interactions across space, something no current theory includes. And this connects to the enormous empty structures James Webb is also mapping. Structures that are doing something unexpected to the universe around them. Between the filaments and walls of the cosmic web, there are voids, regions of space that contain almost nothing, no galaxies, almost no gas, stretching across hundreds of millions of light years. In some cases, these voids are the largest structures in the observable universe, and James Webb, combined with recent large-scale surveys, is revealing that they are stranger and more significant than anyone anticipated. A void is defined simply as a region of space where the density of matter is significantly below the cosmic average. In a universe where gravity pulls matter together over time, voids are the natural result. Matter drifts toward overdense regions, building up the filaments and clusters of the cosmic web, and the regions between those structures empty out. Voids grow over time as matter continues to drain from their interiors. The largest confirmed voids span several 100 million light-years. The Bootes void, one of the most studied, covers roughly 330 million light-years across and contains almost no galaxies in its interior. When it was first discovered in the 1980s, astronomers were so surprised by its size that several checked the data multiple times before publishing. Models of cosmic structure formation predict voids. They are a necessary consequence of the same gravitational processes that build galaxy clusters. But the models also predict a specific distribution of void sizes and a specific rate at which they grow. James Webb and recent wide-field surveys are finding that the distribution of very large voids does not perfectly match these predictions. There are more extremely large voids than the standard model comfortably accounts for, and some of these voids appear to have formed earlier in cosmic history than simulations suggest they should have. One particularly striking finding involves the relationship between void growth and dark energy. In an accelerating universe, voids grow faster than they would in a universe driven by gravity alone. The rate of void growth is therefore a sensitive probe of dark energy's strength. Measuring how quickly voids grew at different points in cosmic history provides an independent test of whether dark energy has remained constant over time. Early results suggest that voids in the early universe were growing at a rate inconsistent with a perfectly constant dark energy. The signal is preliminary. It needs to be confirmed with larger datasets. but it aligns with the other hints from quasar-based measurements and galaxy clustering data. Inside the voids themselves, James Webb has found something unexpected: a small population of isolated galaxies sitting in the middle of regions that should be nearly empty. These void galaxies are forming stars at rates inconsistent with their environment. They appear to have evolved in isolation from the gravitational influences that shaped galaxies in denser environments. If physical constants vary slightly across space, voids are where you might expect those variations to be most detectable. Measuring the atomic spectra of void galaxies provides an independent check on fine structure, constant measurements from quasar absorption. The data is still coming in, but the voids are no longer just the empty spaces between the interesting things. They are becoming some of the most interesting things themselves. And beyond them lies the ultimate boundary, the one line in the universe that no observation will ever cross. There is a line in the universe that no observation will ever cross. It is called the cosmic horizon, and it marks the absolute edge of what any telescope can ever show us. Everything beyond it is, by the laws of physics as we understand them, permanently hidden, and James Webb is revealing just how strange the region near that boundary actually is. The horizon exists because of two facts working together. Light travels at a finite speed, and the universe has a finite age. Light that left a source more than about 46 billion light-years away has not had enough time to reach us, even if it started traveling at the very first moment after the Big Bang. The number 46 billion is larger than the age of the universe in light-years because space itself has been expanding during the journey, stretching the distance between us and distant sources even as their light traveled toward us. Beyond that distance, there is light that set out toward us at the Big Bang but has not arrived yet. There are galaxies, presumably, that are similar to the ones James Webb is observing. There may be structures on scales we cannot imagine. By the best current estimates, the observable universe is only a tiny fraction of the total universe, possibly a negligibly small fraction. That concept has physical consequences for what we observe. If the universe extends far beyond our horizon, the properties of what we see should be close to average properties for the universe as a whole. The Standard Model assumes this. It is called the Copernican Principle, the assumption that our location is not special. But if the universe is not perfectly uniform on scales larger than our horizon, if there are conditions beyond what we can see that differ from what we observe, then what we measure as universal constants and laws may be local properties, values that are true for our patch of the cosmos, but not necessarily identical everywhere. James Webb cannot see beyond the horizon. No instrument can, but it can probe the region near the horizon more clearly than any previous telescope, and what it finds there carries implications for the territory beyond. One specific finding worth noting is the distribution of the most distant confirmed galaxies. They are not uniformly spread across the sky. Certain regions have concentrations of very high redshift objects. Other regions appear comparatively sparse. The pattern could be due to observational biases, or it could reflect a genuine large-scale structure on scales approaching the horizon. Distinguishing between these possibilities requires complete sky surveys at very high redshifts, work that will take many years. What the horizon tells us is that the universe we can study is a subset, a sample. The degree to which that sample represents the whole is unknown and may be unknowable. This uncertainty sits at the heart of the deepest theoretical debates in physics, and one of the most striking implications of everything the telescope has found is that the idea of multiple universes, once dismissed as speculation, is now being taken more seriously by mainstream physicists than at any previous point in history. That is where this story goes next. The multiverse is one of the most debated ideas in modern physics. For decades, it lived at the edge of respectability, an implication of certain theories, rather than a prediction of any observation. James Webb has not confirmed the multiverse. What it has done is make the problems that the multiverse was invented to solve look considerably more serious. The multiverse emerged from inflation theory. Inflation is the leading explanation for why the early universe was so smooth and uniform, and why regions of the universe too far apart to have ever communicated look almost identical. The basic idea is that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing by an enormous factor in an almost immeasurably short time. Inflation works. It resolves several major problems in cosmology and makes predictions confirmed by observations of the cosmic microwave background. The problem is that in most versions of inflation, the process does not stop uniformly everywhere. It stops locally, in our region of space, and continues elsewhere. Different regions of space exit inflation at different times, with potentially different properties. The result is a vast collection of bubble universes, each with its own physical conditions, potentially its own values for fundamental constants. This is called eternal inflation, and it is a direct mathematical consequence of the most widely accepted models of inflationary cosmology. For years, the multiverse was criticized as untestable speculation. If other universes exist beyond our horizon and have no connection to our observable cosmos, how could we ever know? The criticism was fair. Then James Webb started finding things that do not fit the current single universe model. The impossible galaxies, the Hubble tension, the hints of variation in fundamental constants, the anomalies in the cosmic microwave background. Each anomaly can be addressed within a single universe framework if the model is modified in the right ways. But the modifications required are becoming increasingly numerous and increasingly specific. In physics, when a theory requires too many independent modifications to save it from contradictions, that is a signal the theory may be incomplete. The preferred response is to look for a deeper framework that naturally explains what the modifications were trying to patch. The multiverse provides such a framework for some of these problems. If fundamental constants vary across bubble universes, we should not be surprised to find hints of variation near the boundaries of our observable patch. If inflation produced regions with different initial conditions, then the anomalies in galaxy formation and large-scale structure might reflect the specific initial conditions of our bubble. What is confirmed is that the multiverse is now discussed in mainstream physics journals as a framework for interpreting observational anomalies. The cold spot, the Hubble tension, the fine structure, constant variation, all have been analysed in this context by serious researchers at major institutions. James Webb did not create the multiverse idea. By sharpening the anomalies that motivate it, the telescope has given the discussion a new sense of urgency. And there is one more layer to add, because time itself, at the edge of what James Webb can see, behaves in ways that make everything we have discussed so far even more complex. Time does not pass at the same rate everywhere in the universe. This is a prediction of general relativity, confirmed by countless experiments, and now being observed directly in the earliest galaxies James Webb has found. The deeper the telescope looks, the more dramatically time itself appears to run. Time dilation, caused by the expansion of the universe, is different from the time dilation caused by velocity or gravity, though all three follow from the same underlying physics of general relativity. In an expanding universe, the signals that arrive from a very distant, very early galaxy are stretched in time, just as their light is stretched in wavelength. Events that take a certain amount of time in that early galaxy appear, from our vantage point, billions of years later, to take longer. This effect is called cosmological time dilation. It was predicted long before it was observed. It follows directly from the redshift of light. If the wavelength of light is stretched by the expansion of space, so is the time between the arrival of successive wave peaks. A source with a redshift of 2 appears to be running at 1/3 the rate of our local time. A source at a redshift of 9 appears to be running at 1/10 our rate. For years, confirming this effect observationally was difficult. You need objects that change on predictable timescales, like supernovae, and you need to observe them at very high redshifts in enough detail to precisely measure the rate of their evolution. Hubble could do this at moderate redshifts. James Webb can do it much further back. A study published using James Webb and archival data from other telescopes confirmed cosmological time dilation at high redshift at a level of precision not previously achieved. Supernovae in distant galaxies were observed to brighten and fade at the rates predicted by general relativity given their redshifts. The universe, at those distances, does appear to be running in slow motion relative to our own clocks. This is a confirmation, not an anomaly, but it carries significant implications for how we interpret everything else James Webb is observing. The impossible galaxies, the ones that appear too mature for their age, must be understood in the context of time dilation. When we say a galaxy at redshift 13 existed when the universe was 300 million years old, that age is measured in our time, the time of the current observer. In the frame of that galaxy, time was running at a fraction of the rate it runs for us today. The galaxy's own internal clock was ticking differently. This does not resolve the timeline problem. The physics of star formation and gravitational collapse do not speed up just because an outside observer sees them in slow motion. But it adds a layer of complexity to how the comparisons between early and late universe galaxies must be made. And it is a layer that not all popular accounts of the impossible galaxy problem fully acknowledge. At extreme redshifts, the combination of light travel time, time dilation, and the evolving expansion rate of the universe creates a web of effects that have to be carefully disentangled to extract any physical conclusion. James Webb's precision makes this disentanglement more reliable than it has ever been. And underlying all of these observations is a debate that has been building for years in the physics community. A debate about whether the anomalies James Webb is revealing represent actual new physics, or whether they represent the accumulated effect of systematic errors in the measurements themselves. That debate is the subject of the next chapter, and it is one of the most important scientific arguments currently underway. Every anomaly James Webb has uncovered exists in a space of uncertainty. The impossible galaxies, the Hubble tension, the hints of varying constants, the early quasars, all of them rest on measurements that carry error bars, calibration assumptions, and interpretive frameworks built on previous understanding. The question at the center of modern cosmology is whether those anomalies point to genuinely new physics, or whether they will dissolve as the measurements improve. This is not a simple question to answer, and both sides of the debate are defended by serious scientists with substantial track records. The case for measurement error is grounded in the history of science. Anomalies in precision measurements have appeared before and turned out to be systematic errors. Early measurements of faster-than-light neutrinos made headlines before a loose cable was found to be the cause. Indications of a detection of gravitational waves from the early universe were later attributed to contamination from galactic dust. The record of anomalies, quietly resolved by better instruments, is long. For the current cosmological tensions, several candidates for systematic error have been identified and are being tested. In the Hubble tension, the calibration of Cepheid variable stars in nearby galaxies carries uncertainties related to the chemical composition of those stars, a factor that affects their intrinsic brightness, and therefore the distances calculated from them. James Webb has improved this calibration, but not fully eliminated its uncertainties. For the impossible galaxies, the conversion of observed infrared brightness into physical properties like stellar mass and star formation rate depends on models of how stars of different types emit light across different wavelengths. If those models are wrong for the unusual stellar populations of the very early universe, the derived masses could be inflated. Several groups have explicitly explored this possibility and found it can reduce the discrepancy somewhat, but not eliminate it. The case for new physics rests on the pattern of anomalies. Each individual measurement may have a mundane explanation. But when multiple independent measurements from completely different methods and instruments all point in the same direction, statistical coincidence becomes a less satisfying explanation. The Hubble tension has been confirmed by at least 5 independent measurement approaches. The early galaxy problem has been confirmed by multiple telescopes in multiple regions of the sky. The fine structure constant variation appears in independent quasar datasets from different telescopes. Convergence of independent evidence is one of the strongest signals in science that something real is being detected. The most conservative new physics proposals involve small modifications to well-established frameworks, adjustments to how inflation shaped the primordial power spectrum, modifications to how dark energy behaves over time, revisions to the stellar feedback models used in galaxy formation simulations. These can potentially address individual anomalies without requiring the overthrow of the entire standard model of cosmology. More radical proposals include modifications to general relativity on cosmological scales, entirely new forms of dark matter that interact with standard matter in previously undetected ways, and the possibility that the cosmological constant is genuinely time-varying. What is confirmed is that the field is at a decision point. James Webb is generating data at a rate and precision that will force a resolution within the next decade. Either the measurements will converge into a consistent picture that a modified standard model can accommodate, or the pattern of anomalies will sharpen to the point where a genuinely new framework becomes necessary. The next chapter accounts for everything the telescope has already changed permanently, regardless of how the debate resolves. Because some things James Webb has altered cannot be put back. Some scientific discoveries refine the picture. They add detail, sharpen focus, narrow uncertainties. Other discoveries change the picture itself. James Webb has produced both kinds, but several of its findings have already crossed a line that cannot be uncrossed. Regardless of how the anomalies resolve, cosmology will never look the same as it did before this telescope opened its eyes. The first permanent change is the timeline of galaxy formation. Before James Webb, the most distant confirmed galaxies placed the beginning of large-scale structure well over 400 million years after the Big Bang. The telescope confirmed galaxies at 300 million years and provided strong candidates at even earlier times. Every model of galaxy formation now has to account for this. The second permanent change is the severity of the Hubble tension. Before James Webb, some researchers hoped that improved Cepheid measurements would reveal a calibration error that had been inflating the late universe expansion rate. James Webb provided those improved measurements. The gap did not close. Whatever is causing the tension, it is confirmed to persist even at the highest level of Cepheid precision currently achievable. That conclusion is now established. The third permanent change is the observational status of the early universe. James Webb has demonstrated that the first billion years of cosmic history were a period of intense, rapid, and in some ways violent formation, with massive galaxies, powerful black holes, and significant chemical enrichment, all appearing far earlier than previous observations suggested. The early universe was not an infant quietly forming its first stars. It was already a busy, complex system by the time any previous telescope could see it clearly. The fourth change involves dark energy. The combination of James Webb's high redshift galaxy observations with other ongoing surveys has provided new data on how the large-scale clustering of galaxies has evolved across cosmic time. The early results have not confirmed a constant dark energy. They have not ruled it out either, but they have established that the assumption of a perfectly constant dark energy is testable with current instruments, and that the tests are returning results that warrant further investigation. The question of whether dark energy varies is no longer speculative. It is an active measurement campaign. The fifth permanent change is perhaps the most significant in the long run. James Webb has established that the universe near the edge of the observable cosmos does not simply look like a fainter, older version of the nearby universe. It looks different in ways that are physically meaningful. The galaxies are different. The black holes are different. The large-scale structure is different. The behavior of fundamental quantities may be different. The assumption that physics operates the same way across all times and all places is now under observational scrutiny in a way it never was before. These changes are the foundation of the next era of cosmology. Every theory that claims to describe the universe must now account for what James Webb has found. And the new map of the universe this telescope has produced is still being drawn, still adding question marks in places where the old map showed confident answers. Every generation of astronomers inherits a map, a picture of the universe built from the instruments and methods available to those who came before. Each generation adds to it, corrects it, extends its edges. James Webb has handed this generation a map that looks fundamentally different from the one it replaced. And the new map is still being drawn. The most striking feature of the new map is depth. Before James Webb, our confident knowledge of individual galaxies extended back to about 400 million years after the Big Bang. Beyond that was mostly darkness, with only hints of structure detected through statistical methods rather than direct observation. James Webb has filled in that darkness. The map now contains confirmed galaxies from the first 300 million years, with candidates pushing into even earlier territory. The observable universe, in terms of confirmed structure, has grown substantially. The second major feature is detail. In the nearby universe, James Webb's infrared sensitivity has allowed astronomers to peer through the dust that blocks optical telescopes, revealing hidden star formation regions, the cores of dense galaxy clusters, and the environments of active black holes with a clarity that was not previously possible. The map has gained texture, not just extent. The third feature is the pattern of anomalies. The new map does not show a uniform, smoothly evolving universe that transitions predictably from its early state to its current one. It shows a universe with a complex and, in some places, self-contradictory history. Regions of rapid early structure formation alongside regions that look more like the models predicted. Expansion rates that disagree depending on how you measure them. Voids larger than expected. Quasars more powerful than the timeline allows. The new map has question marks on it, explicitly, in places where the old map showed confident answers. That is actually progress. A map with honest question marks is more accurate than one that papers over discrepancies with overconfident models. What the new map suggests about the nature of dark matter deserves particular attention. The distribution of matter in the early universe, as revealed by James Webb's high redshift galaxy observations, is placing new constraints on what dark matter can be. Certain dark matter models predict specific patterns of small-scale structure that are not being confirmed in the observations. Others predict large-scale behaviors that match better. The dark matter debate, which has been ongoing for decades, now has new data to contend with. The new map also suggests something important about the cosmic web's evolution. The web appears to have been more developed in the early universe than expected, meaning the filaments and voids that define it were established earlier and with more contrast than the models predicted. This implies that the forces shaping the web were operating differently in the early universe than current models describe. Perhaps most importantly, the new map is a living document. James Webb continues to observe. Its archive grows every observing cycle. The most distant confirmed galaxies today may not hold that record by the end of the decade. The anomalies being tracked now will either sharpen into clear evidence for new physics or fade as the data improves. The map will continue to change. And at the edge of that map, where the universe fades into the unreachable, sits a question that James Webb has circled without yet answering. A question about what the universe is ultimately doing and where it is going. That question is the last stop on this journey. James Webb has changed cosmology. That is established. But the telescope has also produced something equally valuable, a precise accounting of what we do not know. And the question it has not yet answered is the deepest one of all. The question is this: what is the universe made of? Why does it behave the way it does at its extreme edges? And what is its ultimate fate? These are three ways of asking the same thing. The composition of the universe, the behavior of its fundamental forces at the largest scales, and the trajectory of its future are all connected by the same underlying physics. Get one right, and the others follow. Get one wrong, and the others collapse. James Webb has narrowed the possibilities. It has ruled out certain models of galaxy formation that were previously viable. It has constrained the behavior of dark energy in ways that earlier instruments could not achieve. It has confirmed the Hubble tension as a real discrepancy rather than a measurement artifact. It has mapped the early universe in detail that forces every competing theory to confront real data rather than extrapolated assumptions. What remains is what cosmology always ultimately returns to: the nature of dark matter, the nature of dark energy, the physics of the first fraction of a second after the Big Bang, before any observation can reach, and the question of whether the universe we can observe is a representative sample of a larger whole or a small and possibly atypical bubble in a vast and unknowable sea. None of these will be answered by James Webb alone. The telescope's lifetime is finite. Its mirror cannot grow. Its orbit cannot be adjusted to see beyond the horizon. What it can do is continue providing the data that tells future instruments exactly where to look and what to look for. Several next-generation observatories are being built explicitly to follow up on what James Webb opened. The Nancy Grace Roman Space Telescope, designed to conduct wide-field surveys at infrared wavelengths, will map the distribution of galaxies across a volume thousands of times larger than James Webb can cover. It will provide the statistical samples needed to determine whether the anomalies James Webb found are rare fluctuations or the leading edge of a universal pattern. The extremely large telescope, currently under construction in Chile, will combine a mirror over 130 feet across with instruments capable of measuring the spectra of individual stars in distant galaxies. It will allow astronomers to test the fine structure constant using stellar atmospheres rather than quasar absorbers, providing an independent check on the variation hints discussed in this story. Future gravitational wave observatories will measure the expansion of the universe using an entirely independent method, bypassing all of the current calibration debates. The question that remains is a frontier, and James Webb has done what every great scientific instrument eventually does. It has mapped the frontier precisely enough that the next generation of scientists knows exactly where to begin. The telescope is still watching. The universe is still giving up its secrets, slowly, one photon at a time, arriving from distances so vast that the light carrying them left its source before the Earth existed. And somewhere in the data, still waiting to be analyzed, the answer to the deepest question may already be waiting. We are still listening, and the universe has not finished speaking.